Welcome to this video on analytical solutions of ordinary differential equations. By the end of this video, you will be able to solve some special first-order non-homogeneous ODEs analytically, and also you'll be able to solve nth-order linear ODEs with constant coefficients analytically. So for some simple ordinary differential equations, we can find analytical solutions. So let's consider the following first-order non-homogeneous ODE that has a very special form that we have dy dx plus a function p that is only a function of x times y is equal to, on the right-hand side, another function q that is only a function of x. Now, if we define the function mu of x as being e to the power the integral of p of x dx, then we can look at d mu dx, which is then just the derivative of this defined function, which is d dx of e to the power integral p of x dx. And if we do the integral of that, that is just e to the integral p of x dx times the derivative of the integral of p of x dx, which then is, we copy the first term over, and the derivative of the integral is just p of x, which would mean that since e to the integral p of x dx is equal to mu of x, this would be equal to mu of x times p of x. Okay, so how does that help us? Well, let's multiply the original ODE by this function mu of x. So on the left-hand side, we have mu of x times dy dx, then plus mu of x times p of x times y is equal to, on the right-hand side, we have mu of x times q of x. Okay, so let's look at this mu of x dy dx and copy it over. And then we have mu of x times p of x, but that is d mu dx, right? So we replace this by d mu dx, then times y, we leave that untouched. And on the right-hand side, we have still mu of x times q of x. So now if you look on the left-hand side here, you'll recognize that we can apply the product rule in reverse. So that is just, on the left-hand side, the derivative of mu times y dx is equal to this right-hand side that is only a function of x, the mu of x times q of x. So we can now integrate this. So if we integrate this, we have on the left-hand side, right, the integral of d mu y dx is equal to, the dx is cancelled, the integral of d mu y. On the right-hand side, we have the integral of mu of x times q of x dx. So the integral of d mu y is just mu of x times y of x. Okay, and then we have to add an integration constant, c1. And on the right-hand side, we still have just the integral of the product of mu of x times q of x dx. Now let's divide this equation by mu of x because we're interested in the solution to the ODE y of x. So that means that y of x is equal to 1 divided by mu of x times the integral of mu of x times q of x dx plus c1, this integration constant, divided by the function mu of x. And that is the solution to this particular form of a first-order non-homogeneous ODE. So let's do an example for this. Let's find the solution to dy dt is equal to 4 times e to the power 0.8 t minus a half y. And we need a constraint for this equation, an initial condition. So the initial condition is that y at t equal to 0 is equal to 2. Okay, so we have this ODE here to solve, and the variable names are a little bit different from what was used in the general derivation of the method. So let's just identify them first up. So in the equation here, y is still the dependent variable, right? That didn't change. but the independent variable here is t, time. So t is the independent variable. Right, that corresponds to the x from the general solution formula. All right, so what we'll have to do in order to apply this solution scheme is to bring our ODE here that's given into this particular form. So we'll have to have on the left-hand side dy dt, and then plus a p of t times y, and then on the right-hand side we'll have only a function of t. So that means we have to move this part here, which contains the times y, over to the left-hand side. So this means we'll have dy dt plus 1/2 y is equal to 4 times e to the power 0.8 times t. And now we can go in and identify the individual components. So we have this p here, which would be this guy over here. So we can identify in our naming, right, the variable name for the independent variable is t. So we have p of t is equal to just 1/2. And the q of t is equal to whatever we have here on the right-hand side, which is this, the 4 times e to the power 0.8 t. All right, so we have identified our q of t. Let me just mark this here. That's this guy here. And we have identified our p of t. And with those definitions now, we can calculate what mu of t is, or mu of x here, right? So what is this? Mu of t is equal to e to the power, the integral of p of t, so that's just 1/2, times dt. Okay, so we have to just integrate this. And, well, that's just, right, the integral of 1/2 dt is just e to the power 1/2 t. Okay, so that would be my mu of t. Okay, that's my mu of t. That I can then use and substitute into this solution equation. But in this solution equation, I also need to calculate this integral of mu of t times q of t dt. So let's just write this out once. So y of t, my solution will have this form. 1 divided by mu of t, so that's 1 divided by e to the power t over 2, times the integral of mu of t, e to the power t divided by 2, times q of t, that was my right-hand side, so that's 4 times e to the power 0.8 t dt, integral, plus integration constant c1 times 1 divided by mu of t. So 1 divided by e to the power t over 2. That would be my solution. And in order to determine this, I have to do this integral. So first I have, up front, I have e to the power minus t over 2 times this integral of 1/2 t and then 0.8 t, that's 1.3 t. So the 4 I can pull up front. So e to the power 1.3 t dt plus c1 times e to the power minus t over 2. Okay, so now the integral of e to the power 1.3 t dt is equal to, so first of all we have 4 e to the power minus t over 2, and then this integral is 1 divided by 1.3 times e to the power 1.3 t, right? And then plus c1 times e to the power t minus t divided by 2. Okay, so now we can simplify this a little bit before we apply the initial condition. The 1.3t and the e to the power minus 0.5t combine, so we have 4 divided by 1.3 times e to the power 0.8t, and then plus c1, the integration constant, times e to the power minus t over 2. Now, we also have, over here, we have the constraint, the initial condition, that if t is equal to 0, then y should be equal to 2. And that should help us define this constant c1. So let's just plug this in. So y of 0 is equal to 4 divided by 1.3 times e to the power 0 plus c1 times e to the power 0. So that is supposed to be equal to 2. So therefore we have 4 divided by 1.3 plus c1 is equal to 2, or c1 is equal to 2.6 minus 4 divided by 1.3. So that is equal to negative 14 divided by 13. So therefore our solution to the equation is y of t is equal to 40 divided by 13 times e to the power 4/5 times t, that's the 0.8, minus 14 divided by 13 times e to the power minus 1/2 t. And that is then the solution to this particular ODE, which we could verify by just substituting it in, and we would see that this would solve the actual ODE. So that's one way of finding an analytical solution to one particular form of a non-homogeneous first-order ODE. There are other ways of finding analytical solutions, and one easy approach, or for one particular class of ODEs, is finding analytical solutions for nth order linear ODEs with constant coefficients. So what does that mean? Nth order ODE means that the highest derivative in the ordinary differential equation is the nth derivative. And because of the constant coefficient, that derivative gets multiplied by a constant. So here that constant is just called a sub n, that multiplies the nth derivative of y with respect to x. And since the highest derivative is the nth derivative, we can have, of course, the n minus first derivative, the n minus second derivative, each one of them multiplied by its own constant coefficient, all the way down to a1 times the first derivative, plus a0 times the 0th derivative, so no derivative. That then is equal to, because this can be non-homogeneous, this could be equal to a q of x. But let's look first at the homogeneous case, where q of x is equal to 0. And in that case, we can assume that the solution is of the following form. Y of x is equal to e to the power lambda x. Now, if we take this solution, and that's this assumed solution, and substitute it into the ODE, right, first term would be an times lambda to the power n times e to the power lambda x. Substituted in the ODE, the second term would be a sub n minus 1 times lambda to the power n minus 1 times e to the power lambda x. And so on, right? We have additional terms. We then hit the first derivative after a while, plus a1 times lambda e to the power lambda x, plus a0 times e to the power lambda x is equal to, if it's homogeneous, then this is equal to 0. Now we can divide this entire equation by e to the power lambda x, or technically speaking, we could factor e to the power lambda x out. and then set one of the factors equal to 0. So that would give us, all the e to the power lambda x disappear. We are left with an times lambda to the power n plus a sub n minus 1 times lambda to the power n minus 1, all the way to plus a1 times lambda plus a naught is equal to 0. And that's what's called the characteristic equation. It's an nth degree polynomial equation that will have n roots. Now these roots can be complex numbers though. But I'm guaranteed to have n roots. They might not even be unique. There might be some repeated roots in there, repeated values, but there will be n roots, and I can name them lambda 1, lambda 2, all the way through lambda n. Now with those roots known then, the solution will be the linear superposition of e to the power lambda x, where lambda is one of these roots. So the solution is y is equal to some constant c1 times e to the power lambda 1x plus c2 times e to the power lambda 2x, all the way to the nth root, so c sub n times e to the power lambda sub n times x. Now if roots are repeated, meaning they have a so-called multiplicity, we'll have to do something special. So let's take an example that the root lambda sub I is repeated k times, which means that the solution will now contain, for those k repeated roots lambda I, something like this, the sum from j equal to 0 to k minus 1 of c sub j, some constant, times x to the power j times e to the power lambda I times x, where lambda I is the same root repeated k times. Okay. Now, complex roots, right? These roots can be complex. They must appear in conjugate pairs, which means they can be replaced with a real function. So here's one example for that. If one of the roots is lambda 1 is equal to alpha plus I times beta, where I is the imaginary number, then we must have its conjugate pair as well. So there must be a lambda 2 that is alpha minus I times beta. Now if we plug this into the solution ansatz, right, the e to the power lambda x, we get the following thing. So we get e to the power lambda 1x, which is e to the power alpha plus I beta times x, plus e to the power lambda 2x, but lambda 2 is the conjugate pair, so it's plus e to the power alpha minus I times beta x. And now we can combine these two to a real function that will just be c1 times e to the power alpha x times the cosine of beta x plus c2 times e to the power alpha x times the sine of beta x. That just comes from the definition of e to the power ix. So let's do an example and solve this particular ODE here. So it has the third derivative as the highest derivative. And then there are constant coefficients, minus 4, minus 1, 6, that multiply each one of the derivatives that appear in the ODE. So the ODE is of this particular form. So let's start by actually isolating all the derivatives over to the left-hand side. So we have 1 times d3y dt cubed plus 4 times d2y dt squared plus dy dt minus 6y is equal to 0. And so now this ODE here from the general solution procedure, right, is the form that we have over here now. So let's identify some terms. So the a naught here is the term that multiplies the y, the dependent variable, so that would be negative 6. The a1 is the term that multiplies the first derivative, that would be this one here, which is kind of hidden, it's a 1, right, the multiplier there. And then we can go to higher and higher terms up to the third derivative. And these terms now here appear in the characteristic equation, right? I'm just marking here the A0 and the A1. So we can now write the characteristic equation. Okay. And it starts with a lambda cubed term because this is a third order ODE. So it's 1 times lambda cube plus 4 times lambda squared plus 1 times lambda minus 6, that's the A0, that is equal to 0. And now we have to find the roots of this equation. Well, it's a cubic polynomial, and there are analytical methods of finding the roots of a cubic polynomial. But in a situation like this, maybe we can guess one of the roots that appears here. So what one can do is just try out some values for lambda, simple values, and see whether they would solve the equation. So lambda 0 doesn't work, right, because there's a minus 6. Let's try a lambda of 1. 1 plus 4 plus 1 is 6. Minus 6, that's 0. So I kind of know that one of the roots, one of the factors that I can factor out of this polynomial has to be lambda minus 1, right, because lambda equal to 1 solves this equation. So if I do this, then I get what's left would be lambda squared plus 5 lambda plus 6. Okay. And if I look at this remaining term here, I can factor this as lambda plus 2 times lambda plus 3. So that would be lambda minus 1 times lambda plus 2 times lambda plus 3. And that has to be equal to 0. So I can then read off directly what my roots are of this equation. So I have a lambda 1 that is equal to negative 3, right? That comes from this term. I have a lambda 2 that's equal to minus 2. And we have a lambda 3 that's equal to 1. And I've just sorted them in increasing values. All right, so I've identified what my lambdas are. So I can now plug this in and write the solution. So the solution is y of t is equal to a constant c1 times e to the power negative 3t plus another constant c2 times e to the power negative 2t plus a third constant c3 times e to the power t, 1 times t. And that's the solution to this ODE. And the constant c1, c2, c3 would be determined from constraints that would have to be given. But here it's just the general equation with no constraints. Okay. Thank you for watching.